It's easy to think that getting to space is just about going up, right? Gaining altitude. And if that was all there was to it, yeah, we'd just point the rocket straight up and hit the gas. But the real trick isn't just getting to space, it's staying there. And to do that, you need a completely different game plan.
And this really breaks it down, doesn't it? Trying to go straight up is just a losing battle. Think of it like trying to swim straight up a waterfall. You're fighting gravity head-on, plus you're pushing through the thickest, densest part of the atmosphere for the longest time. It's just brutally inefficient. You burn a ton of fuel just to have gravity pull you right back down. But when you curve, that's the smart move. You slice through that thick lower atmosphere as quickly as possible, and then you can pour all that energy into what really matters, building sideways speed. You're not fighting physics anymore, you're using it.
And that brings us to this just wow. This number, 18,000 miles per hour. That is the kind of sideways speed you need to hit just to stay in low Earth orbit. Seriously, just take a second to let that sink in. It's so fast. In fact, roughly half of all the energy in a rocket's fuel tanks is dedicated purely to getting that insane horizontal velocity. So see, it's not about how high you go, it's about how fast you can go sideways once you're up there. Okay, so how on earth does flying sideways at 18,000 miles per hour stop you from just falling? It seems like gravity should still win, right? Well, to get our heads around this, we need to jump back in time a bit to the 1600s and look at a really elegant thought experiment by none other than Isaac Newton. This one idea is basically the foundation of all orbital mechanics. So Newton pictured this. You're on top of a super tall mountain, way above the atmosphere, and you have a cannon. Okay, step one. You fire a cannonball. What happens? It travels a bit, but gravity pulls it down in an arc and it hits the ground. Simple enough. Step two, you fire it way faster. Now it travels much, much farther before it hits the ground. But here's the brilliant part. Step three, what if you could fire it so fast at what we call orbital velocity that as it falls towards the Earth's surface is curving away from it at the exact same rate. It's still falling, but it never, ever hits the ground. It just keeps missing. And that is an orbit. And that right there gives us the single best definition of an orbit I've ever heard. It has nothing to do with being outside of gravity or floating. An orbit is simply the state of continuously falling toward a planet, but you're moving so ridiculously fast sideways that you constantly miss the ground. When you see astronauts floating on the ISS, they're not weightless. They are in a constant state of free fall, and so is the station around them. They're just missing the Earth together endlessly. So, if Newton gave us the why of orbits, why they work, we have to thank Johannes Kepler for giving us the how. Decades before Newton, Kepler was meticulously studying the planets, and he figured out the 3 fundamental rules that describe the motion of pretty much anything in orbit. You can think of these as the official rules of the road for space travel. Okay, law number 1, and this one kind of shatters a common misconception. Orbits are not perfect circles. They just aren't. Kepler's first law tells us that all orbits are actually ellipses, ovals. And the Earth isn't sitting right in the middle. It's off to one side, at a point called a focus. And what that means, really, is that a satellite in orbit is always getting a little closer to Earth, and then a little farther away, over and over again. And that leads perfectly into the second law. Because the path is an oval, the satellite's speed is constantly changing. Think of it like a skateboarder on a halfpipe. As the satellite swings in closer to Earth, where gravity's pulling on it hardest, it picks up speed, a lot of speed. It's moving fastest at its closest point, which we call perigee. Then, as it swings back out and climbs away from Earth, it slows down, just like that skateboarder going up the other side. It's moving slowest at its farthest point, or apogee. Finally, we've got Kepler's third law, which is just a really elegant relationship between how far away an orbit is and how long it takes. It's super simple, really. The farther away from Earth a satellite is, the longer its orbital journey is going to be, and the slower it's going to travel. So, of course, it takes much more time to go all the way around. A satellite in low Earth orbit is zipping around the planet in about 90 minutes, but something way out in a high orbit could take a full 24 hours to make one trip. So, Kepler's laws are great for the general physics of it all. But what if you need to track one specific satellite out of the thousands up there? For that, you need to be way more precise. You need its unique address in space. And that's exactly what scientists use, a special set of coordinates. This address is made up of a set of just 6 numbers, and they're called the orbital elements. That's it, just 6 numbers. But with those 6 values, you know everything. You can figure out exactly where that satellite is right now, where it was an hour ago, and where it's going to be a year from now. They are literally the GPS coordinates for an object's entire path through space. Now, the names can sound a little intimidating, but they're just answering some basic questions. The first two basically tell you the size and shape of the orbit, how big is the ellipse, and how stretched out is it. The next couple of elements define its orientation. Think of it as the tilt and twist of that orbital path in 3D space, all relative to Earth's equator. And that last one? It's basically a timestamp. It locks in exactly where the satellite was at one specific moment in time, which lets us predict its location forever after. That's the whole package. Okay, so why all this math? Why do we need to be so precise? Because once you understand all these rules, you can stop just getting to orbit and start designing orbits. You can custom build the perfect path for any job you can imagine. It's all about picking the right orbit for the right mission.
And this is where it gets really cool. Look at these examples. If you need a satellite for, say, TV broadcasting, you want it to stay over the same spot on Earth, right? So you put it in a geosynchronous orbit, where its 24-hour period perfectly matches Earth's rotation. Need to provide communications to places way up north, like in Russia or Canada? You use a weird, super stretched-out Molniya orbit that hangs over the high latitudes for hours at a time. For spy satellites or weather satellites that need the same lighting conditions every time they pass over a target, you use a clever sun-synchronous orbit. And of course, for things like the space station or getting amazing photos of Earth, you stick to a fast and close, low Earth